Selamat datang di Politeknik Energi dan Mineral Akamigas yang berlokasi di Jalan Gajah Mada nomor 38 Cepu.
Saat ini kita sedang berada di Gedung Graha Oktana PEM Akamigas.
Sebagai upaya kami dalam mengutamakan aspek kesehatan dan keselamatan kerja, berikut kami sampaikan safety induction Gedung Graha Oktana PEM Akamigas.
Berikut adalah arah mata angin di Gedung Graha Oktana PEM Akamigas. Saat ini saya sedang menghadap ke arah selatan. Di belakang saya adalah arah utara. Di sebelah kanan adalah arah barat dan di sebelah kiri adalah arah timur.
Gedung ini dilengkapi dengan 4 buah toilet. Untuk di lantai 1, 1 berada di arah tenggara dan 1 berada di arah barat daya. Untuk di lantai 2, 1 berada di arah tenggara dan 1 berada di arah barat daya.
Guna menunjang proses evakuasi gawat darurat, gedung ini dilengkapi dengan akses pintu darurat. Lantai 1 terdapat 3 pintu darurat. 1 di sebelah selatan yang merupakan pintu masuk utama, 1 di sebelah barat, dan 1 di sebelah timur. Lantai 2 terdapat 4 akses tangga darurat. 2 di arah selatan, 1 di arah barat, dan 1 di arah timur.
Untuk menanggulangi bahaya kebakaran, gedung ini dilengkapi dengan 9 buah alat pemadam api ringan. Terdapat 6 buah alat pemadam api ringan di lantai 1, 3 buah di sayap kanan, dan 3 buah di sayap kiri. Untuk lantai 2, terdapat 3 buah alat pemadam api ringan. 1 di arah selatan, 1 di arah barat, dan 1 di arah timur.
Saat ini tidak ada simulasi kondisi gawat darurat.
Sehingga, jika ada alarm berbunyi, itu merupakan kejadian yang sebenarnya.
Berjalanlah dengan cepat, tetapi tidak berlari.
Jangan panik dan ikuti instruksi dari petugas.
Petugas akan mengarahkan Anda untuk berkumpul di master point terdekat yang berada di sisi selatan atau sisi barat Gedung Graha Oktana PEM Akamigas.
Demikian safety induction Gedung Graha Oktana PEM Akamigas.
Kami berharap Anda tetap tenang jika terjadi keadaan darurat.
Terima kasih.
Politeknik Energi dan Mineral Akamigas telah berdiri sejak tahun 1966 dengan nama Akademi Minyak dan Gas Bumi atau AMGB. PEM Akamigas merupakan perguruan tinggi di bawah Badan Pengembangan Sumber Daya Manusia, Energi, dan Sumber Daya Mineral, Kementerian Energi dan Sumber Daya Mineral yang bertugas menyelenggarakan pendidikan vokasi, penelitian, dan pengabdian kepada masyarakat di bidang energi dan sumber daya mineral. Ribuan lulusan PEM Akamigas telah banyak berkiprah di industri migas di berbagai belahan dunia. Keberterimaan industri migas terhadap alumni PEM Akamigas sudah tidak diragukan lagi. Menjadi juara di berbagai kompetisi juga merupakan nilai tambah akan keunggulan mahasiswa PEM Akamigas.
Saya, Pradipta Bambang Murtianto, alumni Politeknik Energi dan Mineral Akamigas tahun 2021, program studi Teknik Pengolahan Migas. Berkat berkuliah di PEM Akamigas, hanya dengan waktu tunggu kurang dari 1 bulan, saya sudah bekerja di Lamberjee. PEM Akamigas, jaya, jaya, jaya.
Hai semuanya, perkenalkan saya Deslikim Tamara. Saya merupakan alumni PEM Akamigas tahun 2020 dari program studi Logistik Migas. Belajar di PEM Akamigas tentunya sudah lengkap sekali. Kita akan diberikan lebih banyak praktek dan tentunya akan dibekali dengan sertifikat uji kompetensi. Pokoknya setelah lulus dari PEM Akamigas, kita akan menjadi insan yang siap untuk bekerja di lapangan. PEM Akamigas memang paling oke.
Bertempat di Jalan Gajah Mada 38 Cepu, Kabupaten Blora, Jawa Tengah, PEM Akamigas melaksanakan kegiatan pendidikan melalui 5 program studi yang dimilikinya, yaitu Teknik Produksi Minyak dan Gas, teknik pengolahan minyak dan gas, teknik instrumentasi kilang, teknik mesin kilang, dan logistik minyak dan gas. Sebagai jaminan atas kualitas lulusan, mahasiswa PEM AK Migas juga dibekali dengan sertifikasi kompetensi K3 Migas untuk seluruh program studi, sertifikasi kompetensi yang sesuai dengan keilmuan masing-masing program studi, dan sertifikat lolos uji kemampuan berbahasa Inggris atau TOEFL, serta pembentukan karakter atau kesamaptaan. PEM AK Migas hingga saat ini menerapkan sistem pendidikan berasrama. Oleh karena itu, PEM AK Migas telah menyediakan sarana laboratorium dan bengkel yang lengkap, ruang kelas yang memadai, perpustakaan yang sudah dilengkapi dan dikembangkan ke dalam sistem informasi digital library atau perpustakaan online, geraha Oktana, asrama, restoran, sarana kesehatan atau poliklinik, sarana olahraga, sarana ibadah, dan juga sarana rekreasi. Sebagai perwujudan tridharma perguruan tinggi, selain pendidikan, PEM AK Migas juga melaksanakan penelitian dan juga pengabdian kepada masyarakat. PEM AK Migas, energi untuk negeri.
Assalamualaikum warahmatullahi wabarakatuh. Good morning and greeting to all of us. Welcome to One Day with Experts in collaborations with New Zealand Embassy and Waikato Institute of Technology.
The Honorable Director of PEM AK Migas Cepu, Mrs. Erdila Indriani.
The Honorable, the Representative of New Zealand Embassy, Mrs. Indirawati. Good morning, Miss.
The Honorable, the Representative of New Zealand Embassy, Mr. Keith Yet, which attend this event by online meetings.
And also would like to honorable our wonderful speaker for as a VET Technical Analysis and Design Manager at Waikato Institute of Technology, Mr. Chris Stewart. Good morning, sir. And also thank you for all the participants for coming to One Day with Expert,
which brought the theme
Introduction to the Operation and Monitoring of Geothermal Power Plant.
First of all, let us say thanks to God who has been giving us mercy, guidance, happiness, and healthy so we can attend and participate on today's event.
Ladies and gentlemen, thank you for attending. But first of all, let us introduce ourselves. My name is Demi Pasca from the Oil and Gas Refinery Engineering and my partner,
Safira Putri from Logistic, Oil and Gas.
as the Master of Ceremony, will guide this event.
It's an honor for us to stand here today as the Master of Ceremony. But before we enter the core of today's event, let me explain the agendas first. The first agenda is opening,
The second agenda is opening remarks from Director of PEM Akamigas, Mrs. Erdila Indriani.
The third agenda is opening remarks from the representative of New Zealand Embassy, Mr. Kirk Yates.
And also the core of our event is the presentation from our wonderful speaker from the PhD Technical Analysis and Design Manager at Waikato Institute Technology from Mr. Chris Stewart.
The fifth agenda is question and answer. And the last but not least is closing and documentation. So our participants today in One Day with Expert are mainly from the first and second year student of PEM Akamigas Cepu. So in order to feel their presence, we love to hear their voices. Please give a round of applause for Oil and Gas Production Engineering.
Okay, guys, give the spirit. Please give a round of applause for Oil and Gas Refinery Engineering.
So I want to hear their voices louder. Please give a round of applause for Oil and Gas Mechanical Engineering.
Give a round of applause for Oil and Gas Instrumentation Engineering.
And last but not least, please give a round of applause for Logistic Oil and Gas.
For your information, PEM Akamigas has been making a good collaborations and also cooperations with Waikato Institute Technology in the geothermal pits since 2019. We hope this good relations will continue.
All participants are encouraged to follow the entire event actively because there will be a special gift for those who give a positive or good impression.
Okay, without any further ado, let's get the ball rolling.
The first agenda is opening remarks from Director of PEM Akamigas Cepu, Mrs. Erdila Indriani. For Mrs. Erdila, the time is yours.
Good morning and greeting to all of us, the Honorable Representative of the New Zealand Embassy, Ms. Indarawati, and the Honorable New Zealand Ministry, Mr. Kirk Yates, who is attending in online, and our esteemed speaker, Mr. Chris Stewart from Waikato, and Miss Alia from Waikato, and all guests and faculty member and dear student. First of all, let us express our gratitude to God for His mercy and blessing, allowing to us gather here today in good health and high spirit to participate in this important event, PEM Akamigas One Day with Expert, with theme Introduction to the Operation and Monitoring of Geothermal Power Plant. On behalf of PEM Akamigas, I would like to extend our heartfelt thanks to collaboration with New Zealand, particularly through NSJSTIC, Wintech, for the continued support and cooperation we have received over the years. We sincerely hope that this collaboration will not stop here, but will continue to grow and in advance. We are optimistic that this partnership will inspire our students especially in geothermal energy. Your presence here in Cepu, Central Java, Indonesia, is a testament to your commitment and dedication, and we are deeply grateful to your time and effort. Thank you once again for your invaluable contribution and for being here today. Let's continue to push forward the boundary of green energy and make significant strides to geothermal sector. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you for the wonderful speech, Mrs. Erdila.
Okay, the second agenda is remarks for representative of New Zealand Embassy, Mr. Kirk Yates. For Mr. Kirk Yates, the time is yours. First of all, would like to greeting for Mr. Kirk Yates. Mr. Yates, are you with us right now?
Yeah, makasih banyak. I think I'm online. If you can just confirm that you can hear me okay.
Okay, very well. The time is yours, sir, to...
Makasih banyak. Selamat pagi atau Maria Morena. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera bagi kita semua. Shalom, Om Swastiastu. Namo Buddhaya, salam kebajikan dan kia ora tato, kia tato katoa. Greetings to you all from the New Zealand Embassy in Jakarta. Perkenalkan, saya Kirk Yates, Kansela Pembangunan Selandia Baru untuk Indonesia. Sorry, but unfortunately I can't be with you in person. I'd love to be there in Cebu, but I'm pleased that one of my colleagues, Ibu Ira Indirawati, as Ibu Erdila mentioned, is with you, and the WinTech team, Pak Chris Stewart and Ibu Alia, who are also there with you. So grateful that they're there. I saw you all enter the room earlier. Good to see you. Ibu dan Bapak, aku mihi kia koutou katoa, so I pay my respects to you all. Having joined you online, I am delighted to welcome you all to the training workshop on Introduction to the Operation and Monitoring of a Geothermal Power Plant. If I'm not mistaken, I think this is the third time we have participated within the last 5 years in these types of expert sessions. So we are really glad to participate again on this particular day to share about geothermal energy, and particularly how the process of geothermal operation and how to do the monitoring to a power plant properly. Geothermal energy is one of the key options for Indonesia to achieve comprehensive approach to its national energy development. The rapid growth of fossil fuel-based energy consumption, which is subject to volatility of the global oil market, is the main challenge facing this country's energy supply. At the same time, growing greenhouse gas emissions from fossil fuel use are imposing costs on the economy and society. Sitting here, as an example, sitting here in Jakarta, it may surprise you to know that in the last few weeks, Jakarta has been ranked as the worst polluted city in the world. it has quite an impact unseen on the health and well-being of society in this city. Of course, we're hoping for a bit of rain. We had last night, and some wind to disperse that, particularly as we're working towards an international marathon that's being run in the city later this month. So geothermal energy offers a solution to these types of problems. It is a source of clean, renewable, and environmentally friendly energy for power generation. In addition, as an indigenous and non-tradable energy source, it will advance or enhance the country's energy security by acting as a neutral hedge against fluctuations in the global fossil fuel prices. Look, I'm glad to see the enthusiasm that you all show being here to learn about geothermal. And I couldn't see you all on the screen, but I'm sure you were clapping loudly as the MCs were requesting to welcome everyone there. You're not just participants. You are ambassadors of change, representing diverse backgrounds and study programs. Now, I believe, though, most of you are from oil and gas study programs and have a range of experience and perspectives to bring to today's deliberations. By coming together, sharing insights, and learning from one another, we can collectively accelerate the adoption of geothermal energy in Indonesia. So I urge you to approach this course with an open mind and an eager heart. Embrace the opportunities it offers, take advantage of the knowledge it provides, and together let us all lead the way to a more sustainable future for Indonesia. New Zealand government has and will continue to support Indonesia in its geothermal sector transformation. The New Zealand government, through the Ministry of Foreign Affairs and Trade, has committed to extend cooperation in the geothermal sector for the period 2023 to 2028, with a total grant plan of 15.64 million New Zealand dollars. That's roughly 148 billion rupiah. The program of cooperation is known as Panas Bumi Indonesia Aotearoa New Zealand Kerjasama Program, or PINS. Through PINS, geothermal capacity building program, including training and courses of this nature, will continue. So there will be future opportunities over the next 5 years. Well, I think I've said enough to get things going. It's been a pleasure talking to you. So in closing, I just want to give a few thanks. Thank you for your participation, everyone, in this course. Thank you, Pam Amigas, Ibu Erdila, for your opening remarks, and your team for the great collaboration during this past 5 years. And thank you to the NZ STIGS team, Pak Chris and Ibu Alia, who a lot of behind the scenes and organizational activities to deliver this course today. We look forward to a successful program today, and I strongly encourage you to become active and engaged in this session. Please let me finish by sharing with you a pantun, and happy, although I may not hear it, happy that you all join in the usual way at the end. So it goes like this. Pergi ke Cepu dari Selandia Baru. Jangan lupa mampir ke Surabaya. Ayo belajar energi bersih dan terbarukan untuk masa depan cerah bagi kita. Yeah. So I hope you find that fun. That's my colleague Ibu Ira's creativeness there. So thanks, Ira. here ends my opening remarks. Have a great day and don't forget to have a bit of fun with everyone together also. Ngā mihi nui kia koutou katoa. Salamat datang dan terima kasih.
Thank you, sir. Farewell. Very exquisite closing statement indeed. Thank you, Mr. Cricket, for the wonderful speech.
Okay, so moving on to the main agenda, which is the presentation from our wonderful speaker,
Mr. Chris Stewart.
which will be guided by our marvelous moderator. Please welcome Mr.
Arya Dwi Chandra.
Chandra.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. How are you today? How are you today? Once again, how are you today? Okay. Today we will discuss. We must grateful to God for this morning. We have an opportunity to discuss about the geothermal energy, especially in the great event. We call it One Day with Expert, with the expert from the geothermal energy. As we know, geothermal energy is one of the leading edge in Indonesia. Indonesia is #2 country with the most geothermal production in the world. And our Ministry of Energy and Mineral Resources, one of their priority policy is about net zero emission and energy transition, especially in geothermal energy. We, PEM Akamigas, have a responsibility to create or to provide manpower, especially in energy sector. So we must make sure that our students, all of you in here, have a good competency in energy sector. Okay, I am Arya, and today I am your moderator. And before we invite our expert, he is my best friend. About 4 years, we are together in capacity building, especially in geothermal energy. He is a subject matter expert from New Zealand, support training for geothermal sector and statistics, and representative of New Zealand. And without further ado, we invite our expert. Please welcome Pak Chris Stewart. For your information, Pak Chris is the first Kiwis people who attend in person in Cepu. Firstly, Kiwis people more than 3 times. Ya, Pak Chris. Give applause to Pak Chris. Okay. How are you, Pak Chris?
Thank you for those
Okay.
kind words.
Okay. This is our student from first, second, and third years. And please, student, more interactive to Pak Chris. And I hope in this discussion we'll have a lot of benefit for us. So Pak Kris, time is yours and stage is yours.
Thank you. I'm going to come down here because I feel a long way away. And that's not how I do things. What I will say to you, how many here are really glad you woke up this morning? Because I am. Yeah. And do you know why? I'm with you. It makes it better. Okay? You got to think about that. Every time you wake up in the morning, people haven't. So be glad you've woken up. However, a little bit about me. I am an electrical engineer. Okay? I work in the manufacturing sector most of my life. You know what manufacturing means? What does it mean? Simple. Raw product in, product out. And in that manufacturing process, you change the product. Steam, geothermal in, electric power out. Is that right? In, out. Let's worry about what's in the middle there shortly. Because it is complicated. But it is about having a little bit of interest in it. Now, my understanding is there's a few technical issues, which is fine. You know why? It's called we go with the flow in New Zealand. In other words, it doesn't matter. The sun will rise tomorrow. Is that right? You've just been told the sun will rise because you get up in the morning. So let's keep going. Just for your sake, I've been working long before any of you were born. Is that right? Probably long before they established several geothermal wells in Indonesia. I was actually born before they established the first geothermal well in New Zealand. And I was involved in electrical energy from that time. I studied in 71, but I was employed in 71. Now there's a scary thought, isn't it? My study was in the workplace. I did night classes and Saturday, Sunday while I studied my degree. Okay? So that's a little bit about me. Anyhow, oh, I do have a couple of other things. I do play that sport called rugby. Who's heard of that? It's a bit like futsu. You've heard of that, haven't you? You crash into each other. You hit the wall. You bounce off. I know, because my grandchildren play it in New Zealand. Rugby's a bit different, but you still bang into people. You bounce off people. And you have fun. That's what sport's about. Okay, so we're here to talk about geothermal. My question to you, just a quick one. How many here have actually been to a geothermal site? That's all right. I know you're studying geothermal. I just want to check your knowledge in terms of that. Because geothermal have two processes. There's a process, what they call upstream and downstream. Is that right? So what's upstream? What does that refer to? Come on, you're in oil and gas. If it's upstream, what's it refer to in oil and gas? Reservoir? Where the oil comes from? Because downstream is the refinery, isn't it? Okay. And geothermal, downstream is the power plant. Upstream is the steam field. Same thing. Okay. Difference being Does anyone know where the steam actually comes from? Is it like oil? No, it's not, is it? It doesn't come from a massive big reservoir full of oil. It comes from porous rocks in the ground, not far away from the molten lava that keeps New Zealand, the world hot in terms of that. And we trap that steam and bring it under pressure, like oil, out. Okay. So we've got to think like that. Now, let's go back to renewable energy, because that's what it is, isn't it? It's renewable energy. Is solar renewable energy? Wind? Hydro? What happens when the sun's not shining in solar? What happens when the sun doesn't shine? Solar doesn't work, does it? It comes from the sun, moving electrons inside a panel. What about wind? If the wind doesn't blow, what do you got? No generation, is it? If the wind blows at a gale force, do you know what they do? They stop the blades from turning. Why do you think that would happen? Now, this is a question, technical question. Why do you think that would happen? They stop the blades from turning. It's because the blades spin so fast that it blows the turbine and the bearings apart. Therefore, you have one of those big blades now that could just fly off into the sunset. Okay? What do we do with geothermal? We re-inject it, is that right? Therefore, we're putting the source energy back into the ground to be reheated. That's why it's called a base load. You can keep it going the whole time. Okay? So that's why a lot of people are going that way. So in New Zealand, not like Indonesia, where Indonesia is the second largest country in the world with potential reserves. The word is potential. How you use that over the next decade is whether you become the major contributor of geothermal electric power. New Zealand is nowhere near that, but we have one thing in common. We live on the Ring of Fire. You know what that is, the Ring of Fire? Goes around the Pacific Ocean. Is that right? Where all the volcanoes sit and comes straight through Indonesia, straight through Java, all the way down, misses Australia altogether, big country like Australia, goes across a little bit to an island and hits that, and then turns and comes straight through the middle of New Zealand, called our Taupo district, and then disappears into another area. And it's around the Pacific Ring, isn't it? Right around all those countries. So any country that has volcanoes and more than one volcano is on the Pacific Ring of Fire. Okay, so you're on the Pacific Ring of Fire, we're on the Pacific Ring of Fire, and we capture that. So let's start the presentation. Oh, it's already started. If we just go back a bit. Go back, backwards. Back. Righto, let's go from there. So, we just turn it on. There's the very first geothermal generator. There's your first plant. 10th, Italy, 1913. That's New Zealand's in the 1958. That's what it looks like today. If you just click on that picture, one in the middle, just click on the one in the middle. Gone a bit too far. Never mind. Okay. So let's step back. So 1958, New Zealand built the first one. And what year did Kalimanjang get built in Indonesia? 1960? 61? Built by New Zealand government and a deal with the Indonesian government. So that's when your first geothermal power, that's still running today, okay? But what we want to look at is what does currently run. So if we just open up that YouTube clip here.
Collaboration is key for team success. With ClickUp, you can easily manage your team's tasks and timelines in one.
I want you to look at is the keywords underneath it. No words, Okay. So interesting. It's about several pieces of equipment, doesn't it? Right from the very start, where we had the boreholes and the mufflers. If we didn't have that, there'd be one heck of a lot of noise. Okay, because that's just steam coming straight out of the ground. Who's ever been to a field where there's steam rushing out of the ground at a high pressure? Makes a big hissing noise. Okay, then it goes into pipe work and gets transported across several different kilometers of land till it finally gets to the power generation unit. But before it hits it, it's got to go through a separator. Did I get that right? No, she's not watching. It's all right. A separator. You know what a separator is? You have in the oil and gas? Probably to take out the minerals and the ash and other types of things you don't want in oil, which would be water. In the case of geothermal steam, it's about eliminating water. I don't know what you know about water, but it has a devastating effect on a turbine. So we put it through a separator. We do take minerals out, and then we use those minerals, which is called brine, and we get rid of it. Okay, so we separate it. So the only thing coming out of the top of the separator is pure steam. That steam is what we feed to the turbine. And that turbine uses that steam like every steam turbine in the world and causes what? A rotational mechanical energy called the turbine shaft is turning at around about 3,000 to 4,000 RPM. Can you comprehend how fast that is? Considering that your car will only maximum do probably what? If you stick to the speed limit, I know no one does. Probably about 80 Ks, 80 kilometers an hour. So you can travel 80 kilometers an hour if you can hold that speed. We're doing 4,000 RPM, revs per minute. So it's a considerable amount of mechanical energy. That mechanical energy is then used to turn what? The generator. Have you talked about electricity? Everyone knows you must have a magnetic circuit for electricity to conduct, is that right? Which is why, you know, you sit down and you scrub your feet when you got woolly socks on like this, and you walk behind someone's ear and you get an electric shock and you go, yes, got him. Hey. Or if you're hopping in the car, sometimes you go, ugh, because you got a shock of the car. Who watched the lightning storm the other day? Oh, you weren't in Jakarta. I was in Jakarta watching a lightning storm. The big bit, and bang, hit the ground. Hit somewhere in Jakarta, I don't know where. Thousands and thousands and thousands of voltage hitting straight down, boom. Okay. That's what electricity is. That's how dangerous electricity is. Okay. Here's an interesting fact. Who's got a cell phone on them? And if you don't put your hand up, I know you're telling lies. Who's got a cell phone on them? Hands up. Don't be shy. Here's a scary thought for you. If everyone didn't charge their cell phone at night, everyone in the world, you can turn a nuclear power plant off. Are you aware of that? One nuclear power plant in the world feeds all the battery charges of a cell phone. That's how much energy you're wasting. So you can do something on the phone. Talk to your friends, send them a WhatsApp, all that sort of stuff, eh? You got to think like that. Energy comes from somewhere to drive your phone. Your phone's got a battery. You've got to put the energy back into that battery to get it to work, don't you? Keep thinking like that. That's what energy is. You can't destroy energy. You can only Move it. You've got steam coming out of the ground at 4, 5, 8 bar, temperature roughly around about 170, 180. You can't destroy it. You can only use it and some other force. Okay? In terms of that. So that's what we're talking about. So just think about next time you plug your charger in, how much energy is it using? And what you're talking about is minimal, isn't it? But if everyone in the world turned it off and didn't charge for one whole night, they can turn a nuclear power plant off. We crave power, don't we? In terms of that. So that goes there. Then from there, it goes off into the condenser. Who saw the word condenser come up? The condenser is the used steam that's been pushed through the turbine. And then we're sitting there going, so what are we going to do with that steam now? It's hot. Even if it comes out at about 4 bar, it's still roughly around about 130, 140 degrees C. Okay, it's really hot. So we can't re-inject it at that temperature. We have to send it to the cooling towers. Is that right? You saw the cooling towers? All that little steam coming out of the top of them? It's not steam, it's hot air cooling down because the steam is going down through and cooling off, so that goes back to water, which enables us then to re-inject it. So that's the fundamental behind that. And as a operation, and you are the operator, you have to control that whole process. You've got to know what the control valve is doing on the steam field. You've got to know what the steam field's doing because it's got traps in it to make sure the steam is still pure. You've got to know what the separator's doing. You've got to know what the turbine's doing. You've got to know what the generator's doing. You've got to know what the power is doing as it gets transferred out to the grid, which is called in Indonesia PLN. And then you've got to understand what the regen system's doing. So that's what we're talking about.
Do you need a pointer?
Oh.
The pointer and
So what do I do here? That just moves the PowerPoint on, does it?
the pointer is this one, and if you want to go to the next slide,
oh, okay. Thank you. Perfect. Thank you. Okay. All right. So here's what we talk about. I know it's hard for you to see. Okay. Let's talk about process control. Who's heard of that word, process control? If you're in oil and gas, it's critical. You may not have studied it yet. Process control enables you to control something from a computer. Okay? Typically, that's the pointer. Oh, there it is. You're not going to show. That's all right. Typically, you as the operator would do it. Nowadays, okay, we do it a different way. But we have to control individual pieces of equipment, the various systems that operate the plant. We'll talk a bit about what that means. The entire plane, in other words, the entire plant, and the interface with the electrical grid system, because it has to be interfaced with the electrical grid system in terms of that. At the same time, we're talking about safe manner, product safety, plant reliability, and with the production specifications, because there's always a specification on the energy you're making. Okay. So there we have a fancy little thing. So today, this little room here which is an actual control room of Ngā Tamariki power plant in New Zealand, operates the whole field. Now you notice there's only one person there. In New Zealand, only one person controls the plant. Not because we're smart and we have technology, because the technology in here is the same as you have here in Indonesia. It's because, as I tell to people, New Zealand has only got 5 million people. Can you imagine that? 5 million people? Considering how many people in Jakarta? Last count was 28 million. All of New Zealand, which is as big as Japan, has only got 5 million people. So we can't keep employing people, whereas in Indonesia, you have to employ people to give them an income. We have to shed our responsibilities. Okay. Oop. Oh, there we are. All right. So, bit of a complicated slide, but this is how it works. Okay. There's your control room where you sit. There's your plant. All of this is what you in the control room is starting to operate. I liken it to a car. Who drives a car? Anyone? Who drives a motorbike? Anyone? I know you all do. Okay, last time I was here, a whole lot of people at the end of the day hopped on their motorbikes and drove out to where they live. Okay, so I know you do. Okay, now, my question to you, who turns the wheel of the motorbike or the car? Who turns the wheel, or do you go straight into the wall? The driver does, doesn't he? The guy that sits on the front. So who's controlling the motorbike or the car? The operator. Not the driver, the operator. In the terms of what we're talking about. It's the operator in terms of that. And they're the people who you put your trust in to operate. Is that right? And if you have a crash, you just tell the operator you don't want to drive with them ever again. Okay? But you're the operator. Now, as an operator, I'm going to ask you a question now. How many people here have a little voice in their head talking to them? A little voice is saying, this is getting boring, or it's saying, am I speaking too fast? Am I losing, is he losing the slang? I can't keep up with him. Okay, that little voice is saying that. I catch the odd word. I'm looking at my phone. My friends text me. All those things, isn't it? Because if that little voice isn't talking to you, one or two things has happened. You're either asleep or unfortunately you've died. So anyone who says that voice isn't speaking to me, they're in trouble, tell them. Okay? When that voice speaks to you and you're driving your car and you're driving your motorbike, and it's a voice and you want to answer and someone's behind you, do this, don't you? What's happened the moment you do that? Physically, in you as a person, what's happened? You've taken one of your critical senses, called your eyes, and off the road like that. Is that right? Like that. You have no idea what's happening out here, do you? You think you do because it was clear the moment you did that. But you have no idea. Is that right? You just hope that you turn your head back at the right time. And then you have to hit the brakes. Okay? That's a sensor. Now, here's another scary thought. And I keep telling people this, don't I? How many sensors do you have? Core sensors. Touch, sight, we just talked about. hear, taste. What's the fifth one? There's 5 in there. There's also a 6th one. Do you know that? It's called common sense. So why do you look behind you when you're driving on the road? Common sense didn't work. I'm looking. We are controlled by them. Everything your senses do, of those 5, the whole lot, your brain remembers you've seen it, you've heard it, you've tasted it, you've touched it, you've felt it, all that. It remembers it. Your issue is you have no idea where you've stored it in your brain. So you can only recall the most worst thing that's ever happened to you. And you've had an accident, you've fallen off your bike. We don't remember the really good touchy-feely stuff. We only remember the real bad stuff that happened to us. I have no idea why they do that. So that's what we're doing here. We've got to learn that there is a plant up here. We've got to learn. And that plant has a whole lot of field devices. It has a whole lot of switchboards and motor control centers. It has a thing called a programmable controllers. They can be local, programmable logic controllers, distributive control systems. And on top of all that sits a operator interface that enables you to see that data coming at you, okay? So that's what we're talking about when we go, what are you doing when you're operating a control plant? We're not even talking about anything. We're just talking about what do you need to do in terms of that. And I don't know this will go. That's right. We'll skip that one. All right. So here's you as the operator here. And you've got to look at a whole lot of stuff that's happening in here. Is that right? And you are approximately 5 kilometers away from here, where your steam field bore is. What do? Do you hop in a vehicle and drive all the way down there? Check the reading, write it down, hop in the vehicle, drive all the way back and make the change? Or in today's world, do we put a sensor there that tells us what the pressure is, that tells us what the flow is, which comes up on our screen back in the control room, enabling us to control. That's what it's doing in terms of that process there. Okay, so that's what we're doing here. Here's all the thoughts that we have to do. What is the pressure at the steam, at the wellhead? What is the temperature in the separator? All right, we have to think like that. Is the lubrication system turned on? The lubrication system enables a turbine to rotate. There's no lubrication on the bearing. A catastrophic failure will occur. What that means is a tremendous explosion on the steam turbine. Just like a crash in your car or your motorbike, if that's not working. All this data, okay, all that data doesn't like it the right light, does it? That's all right. All that data, okay, is coming into here, into your brain. Nowadays, it's coming into the computer. Now, my question to you, who here loves playing games on a computer? Who loves playing games on a computer? You play it all the time? You have fun with it? It's exciting? There's an Olympic sport about to come into the Olympic Games called gaming. Were you aware of that? Okay. Don't ask me what games they are because they're just one particular game because everyone's got to play the same game to get a winner in terms of that. But it's an Olympic sport now. There's a scary thought. Get a gold medal. Okay. And what it does, it activates your brain, doesn't it, the whole time? You get excited. The brain is ticking over. It's trying to do things. And your brain is going faster than what you can hit the keyboard. Is that right? And when you get very angry, you start hitting the keyboard. Is that right? It's not the keyboard's fault. Okay. It's the program to run's fault. The program that set up that computer program on your screen hasn't taken into account how fast your hand's going to go like that. And that's what we mean by when you program, in terms of that. Okay, so now we want to talk about key technical documents. So these are some of the things we've got to think about. Who's ever heard at this stage in your study of a heat mass balance diagram? No one? To design anything, steam field, power plant, oil and gas, to design anything, what do you need to know before you start the design? What's the key thing you need to understand? Why are you drilling a hole there in the first place? Is that a key thing that you think the world would work out? So why are we drilling a hole down here when it's going to cost us anything up to 12 million US just to drill a hole? And that's an exploratory hole. There's no guarantee you're going to find anything. That includes oil, that includes steam. But you can't design a plant if you don't know where the reservoir is. What's in the reservoir? Okay. So oil and gas is the same. You've got to re-drill a hole or you're exploring for oil. What's in the reservoir is what you're trying to work out. Same with the steam. What's in the reservoir? What am I going to pull out? How much pressure is it? And that determines what you can build. All right. So the heat mass balance diagram in terms of steam is vital and critical over here. All right. So that's what all this is about. Now, it talks about here steam to unit 4. So that's the entrance level of steam into the steam line. And they want it at a roughly 4,640,000 litres, or vapor as they call it, coming in out of the well. From there, they can redesign the plant. And as you go through this heat mass balance, you see there's steam to unit 4, steam to turbine, steam to all these things here, okay? Now, what it's saying here is that steam to unit 4 and steam to the turbine. So unit 4, that's the overall. But as you go through the steam to turbine, what do you know? Who has ever watered the garden or stand there with a hose? And if you kink the hose, what's going to happen to the pressure coming out of the hose? Better still, who's ever kinked the hose while someone looks at it and you let it go and they hit them in the face with the water? Who's ever done that? I see some smiles, so some of you have done it. It's a bit of fun, isn't it? How to get someone wet. Kink the hose, stop the water flow, tell them to look at the water flow, have a look. When they're looking at it, let it go, straight in their face. First thing we teach our 2-year-olds. Okay? How to not do things that your parents tell them. All right? So that's what we're doing. So for every time you have a piece of equipment in the steam line, you are reducing the pressure. So we need to take that into account. Okay? Who's ever heard of a process flow diagram? Doesn't matter. That tells you what each major equipment is, and it tells you what the flow should be at any given time. Okay? And your HMI, human machine interface, or your screen, as in your computer screen in front of you on your phone, that can only give you the data that it's given. It gets the data from one of these. Right, so there's a sensor where you send data to your application. Okay. Who does instrumentation? I heard a few yells. Where's instrumentation, people? No one here now. You're all gone home. Hey, where's instrumentation? It rules the world. Come on, be excited. Nothing works unless instrumentation works. It's all the sensors. We're sensing things, isn't it? Okay. So we have a PNID. And here's a drawing. Here's all your sensors, all measuring. And that measurement goes off to a computer and it sends back its answers, doesn't it? And you're monitoring it in terms of that. Okay. Here's my favorite one. Who knows all about electrical drawings? Single line drawings, all right, of the plant. So for everything that requires the energy, and you've got them here, we've all seen people playing with this morning, okay, how that works. And importantly, how you keep the people safe. That's very important in that process there. And there are other documents. Let's just keep moving. Okay, who's heard of a block diagram? I think there's some people getting a bit tired here. You know when you stand up the front and you look out over, you cast your eye, you can see people and their expressions. And you can see people doing this. Or you can see people going. Okay, you can see everything. And at some point, if you're in a training session, which only got about 10 or 20, you can actually stop and say, let's take a 5-minute break. Everyone walks outside and come back with fresh air, isn't it? Okay. Just a little thing there. Okay. You got to keep thinking that. So I got to keep this interactive. I've got to keep going. I've got to keep doing. How do I do that? I move. Why I do this? And you're going, what the hell's he doing now? Hey, I'll get up. Look at what he's doing. Okay. Got to keep you active. All right. Block diagram. Here's a question. Do you actually know what that means in terms of operator? This is why it's so important. You understand how a block diagram works. Here's a block diagram right here. These 4 chairs. All right. Product in. Product out. Is that right? Tell me. If I have 6 bar coming in here, product in. This is a steam field. What do you think I'll get here coming out of this chair? What do you think? What do you think will come out here? Something less than 6 bar, because in here is a process and a resistance. So that now becomes the new input to here. Okay. Just keep thinking, process, you're an operator, you're watching what's happening. So you've got less than 6 bar going in here. This is another process. What's going to come out here? Less again. Because in here, you're using energy. And you may cause it to go somewhere else. Okay? Same here. And as you go down further, what you get out here is not 6 bar. What you get out here is what's left as this all gets used. Okay? And that's the key that we're talking about here. So a block diagram may look insignificant to you, but for someone like me, that's really critical. Okay, here input to the steam turbine. I don't say what pressure it is. I said in there is an input to steam turbine. Here, it's an output to rotational force to the generator. So the steam turbine has changed. And that's the rotational force now on the generator to produce electricity. Is that right? So that becomes the output from the turbine, but the input to the generator. If that doesn't meet the specifications that it's required, then we're not going to get the power that we require. And that's the role of the operational staff. Make sure that everything they do, every piece of equipment, no matter what happens, you know exactly what's happening. Hence why in New Zealand, the operators paid more than any electrical, mechanical, instrumentation engineer on site. Paid more. Roughly, if you can calculate in brain, about 140 to 200,000 New Zealand dollars per year. A lot of money, isn't it? Okay, in terms of that. But that's to understand that. So, for those of you who do instrumentation, have you seen this? Okay, I don't know what year you are in your studies. It's called typically a block diagram of a control loop, is that right? And it's called a closed loop control, is that right? And it's got all these different points in here that makes things. So there's your set point, okay? The ultimate is what we want is to control that variable out there and how we do that. I won't go through that because if you're not working in it, you'll have a little bit of an understanding of what's happening. What it means though, here's the story, okay? You got a piece of paper? Just a little piece of paper from a book. I'll just get my able assistant to hand me something. Yeah, that'll do. Right. Beautiful piece of paper, isn't it? Beautiful. Okay. Here's what you do with it. She's aghast now. I have made a throwing device. Is that right? Made a throwing device? And I'm going to throw it. And I'm going to try and hit that TV. You reckon I can? Reckon I can? All right. Here we go. Did I? Here's a question for you. What happened when I let go of the piece of paper? I had no control of it, did I? Absolutely no control of it at all. I could take an aim, I could reach back, and I could throw where I'm pointing, but I had no control once it left my hand. That's what they call open loop. You aware of that? I get no feedback. Open loop control is when I get no feedback. Sorry about that. All right. Can I get any feedback on that piece of paper? No, I can't, can I? There's absolutely nothing. Excuse me a minute. Can I? I have absolutely no control over it. So open loop control is when you have no control of what you've set. I can set a set point. I can take aim. I know how far I've got to throw. So I use my internal muscles. Who's played darts or who's played billiards or snooker, 8-ball, whatever you call it over here? I have no control. Who plays tennis? You have no control once you hit that ball where that ball goes. Baseball's the same, isn't it? Pitcher throws up, throws it at you, you're sitting there, you hit it. You have no control where that ball goes. If you're playing soccer, you have actually no idea where that ball's going to go once it leaves your foot. Because you've got to take into account a whole lot of variables. Variable number one is the environment you're playing in. Okay. What are we playing in? What sort of environment? Is there a high wind? Is it raining? Is it heavy? Is it sunny? All that comes into it. Okay. That's what open loop's about. You have no control. And this is a closed loop control where you have lots and lots of ways that you can control it because you're getting feedback the whole time. That's what closed loop control is doing. And that's what we use in our geothermal power plants. For example, when you go home tonight and you're sitting in your dorm and you go, DJ, can someone turn the light out? Or you just say, can you use your open loop switch and turn the light out, please? Because your lights are an open loop circuit. Off, on. You've got no control of electricity, have you? PLN has complete control of the electricity. You're just reliant on the transformer to give you power. And you're making the assumption that the power is going to get there when you turn the light on, okay, in terms of that. So that's what we mean by those two types of control. Right, so what we've got to think about is we want to make sure that we are working and using plant indication, alarm monitoring, and control for specific equipment. And this is what it's looking at. Local controllers, these things here, okay, are automatic systems. So liken that to your brain when you get up in the morning and you go to the hand basin and you turn the hand basin on and you put the plug in and you sit there and watch it fill up. Is that right? Is that what you do? And as it gets closer and closer to the top, you get your hand and you turn it back, don't you? Until it turns off. How many of you have turned it on, put the plug in, and walked out to do something else, come back and the water's flowing over the hand basin? Because it doesn't turn itself off, does it? Okay? But that's what you're trying to do. So what we've got here is a sensor way out here. That's the product. So if you had a sensor in your hand basin, you'd be able to get it to come back, measure, change it. In here is a mathematical equation that works out your set point, what the temperature is reading, or the flow, or the pressure, and sets a change to the controller. And you are, as an operation, monitoring that the whole time. Now you got to remember, I'm talking one situation. A geothermal power plant will have thousands of these, literally thousands. And you're monitoring and operating the whole lot in terms of that. Okay? Now, like anything, any sensor comes out, you've got to get it into a language that the controller understands. So there's a transmitting device. Once you get into that language, then you can tell the valve what to do. So you sense it here, and the valve makes a corresponding change here. Almost instantaneous from your perspective. But for you, if you're in operations, you need to know what's happening. Because if something goes wrong with your sensor, that's where the fault will occur, and that's where an alarm will go off. And alarms are things that can be ignored, is that right? I see it all the time on the roads in Jakarta. Sirens come past and everyone just sits there. In New Zealand, we all get out of the way. It's either that or suddenly a big horn goes, to try and stop you from doing it. Okay? In New Zealand, that is. All right, so alarms are there. So there's two ways we do it. There's three ways we do it. We have local controllers. Now, who's got a hot water tank? in their house. Give you hot water. Did you know that's a computer? Were you aware of that? Every time you use hot water, you put cold water into your hot water cylinder, is that right? Doesn't matter whether your hot water cylinder is a big one, small one, any one, little hand one, and it's got to heat it up, is that right? Okay, so that's what you're doing. And it's saying to you, okay, man, let's heat it up. If you take water out, water's going to come in. Then you have to heat it up, okay, to get it back to temperature. And if you're the last person in a family of 4 children, like I am, and you go in for a shower and they've had one before you and they've had an hour each time, guess who gets the cold shower? Because the hot water tank takes X amount of time to heat, doesn't it? So you put more water in, then you take in, okay, you're going to get cold temperature. That's standard heat, is that right? If you had a hot drink, who has hot drinks? Put cold water in it, milk in it, it's cold, what happens? Temperature goes down until it reaches equilibrium, as they call it, or equal. But the temperature of the heat has dropped till everything is equal in terms of that. So that's what we're trying to do there, okay? And we use a simple thing like a hot water there, okay, in terms of that. Here's what they use now. I mean, that there's just a little switch, but look what we got now. Massive big flash. This whole thing here, probably $1,000. This thing here, you wouldn't get much change out of 8,000 New Zealand. It's not just a pressure sensor here. It has a whole computer in there. The computer in there is the same computer that's driving your phone, as in the microprocessor chip. It's the same computer chip that's inside your computer, okay? That's how powerful that instrumentation device can be in terms of that. And that sends signals away. All right, so okay, we'll just keep moving, won't worry about the video. So here's what you're doing. So if you're in sensors, as we're talking about, are used for indication and monitoring. They're telling us what's happening. So that's your eyes. What else is it? You feel, touch, isn't it? What else? Ear. What else? Taste. Smell. Okay. Those are all input signals coming into you that your brain is saying. I don't know if you guys have been watching Australian news, but they've had a huge explosion in one of their main towns and destroyed a complete building. They had 7 people in it. 1 person died. That's sad in itself. But now the people are saying we could smell gas weeks before it went bang. Now here's a scary thought. The authorities did nothing about it. We can smell gas coming out. Go around with the gas stick. No gas. No gas. Whoops. Bang. Okay. Real tragic incident, but very avoidable. As an operator, you have that control, so you cannot ignore an alarm. If you have an alarm on anything, be it in your oil and gas refinery, or be it in your geothermal, or be it wherever you're doing it, a catastrophic failure is worth millions and millions of dollars to the owner, much let alone to the environment, much let alone to possibly people, etc. So there's huge responsibility on you in terms of that process there. Okay, so your sensors are everything. You need to look at them, read them. Ones we use, typically flow, temperature, level, pressure, and importantly in rotational manufacturing, vibration. That's the only way we can measure if something's rotating. All right. You do realize that the world vibrates. It's rotating, isn't it? It rotates around and around, get you 24 hours. It rotates around the moon. Sorry, not the moon. It rotates around the sun. Takes you a year. Is that right? Simple. Would have learned that at school. Okay. Anything that rotates, in other words, this world is vibrating. It's just that our bodies are so used to what that rotational force is, isn't it? We don't pick up the world as vibrating. Unless there's something happening like an earthquake or a major thing like that. Then we pick up the difference. Okay. And the plant the same. If you've got a piece of equipment rotating, then you ignore its standard process. But you soon know when something is gone out of whack with vibration, because once it starts going out of whack, you feel that vibration increase. Same with earthquakes in terms of that. That's a simple analogy there. Temperature is the same. Level, we all know temperature, something hot, hottest, coldest, comes out, different scales. Okay, level, instrumentation. How do you measure levels? How do you control? So you're controlling the level of tanks, you're controlling levels of, in terms of geothermal, of what the recovery water is versus what is the hot water level. So the bottom of your cooling tower, there's a water catchment. You've got to maintain the level there to be a certain level. Same time you're measuring the temperature of it, make sure it's the same temperature. And at the same time, you're measuring the pressure, because if it's in a natural forest, then it's going to be blocked up with debris from the trees and the dust and ground. So all that's measured in terms of that process there. Okay, pressure, turns that, and vibration. Then you got your what we call the final control elements. Okay, what are you controlling? It could be a pneumatic valve, a hydraulic valve, a solenoid. It could be electric motors, or it can be large control valves. Okay. For those of you who are looking at this, you see a little man here. Okay. That there is a centrifugal pump. Real size. That man is standing there to show you how big that centrifugal pump is. It's called the hot well pump. It's designed to take water from the bottom of the condenser to the top of the cooling tower, where it goes into the cooling tower and drops through spray nozzles to help disperse the temperature. Okay. It's a high voltage motor, around about 3,000, 4,000 volts. And it's very low speed. It travels roughly around about 700 RPM. But it's critical. The biggest shaft I've seen from there to there, for me, is 8 meters. The biggest shaft, longest shaft, 8 meters. Can you imagine how long 8 meters is? So we just go here. 1, 2, 3, 4, 5, 6, 7, 8. 8 meters. It's a long way, isn't it? 8-meter shaft. When you go, mechanical engineers, when you go back, hey, think about that. Think about your shaft on your little pump that you got there, maybe max, maybe 900 millimeters. That one's 8 meters. A long way. And it's in the ground. There's a vertical pump in terms of that, okay? So, critical piece of equipment, as too is the cooling towers. Right. Now, let's get to the real core of it as an operator. How do we control? So how do we control what we're trying to do here? Okay, so if you come over, look over here, I'll just move over here because I think this side's getting a bit restless and they're missing seeing me. Not really, are you? Okay. So this is what the system is, okay? All these computers, all these PLCs, all these devices. There's your DCS, distributive control system. I'm not going to ask you if you know the difference between these yet, because I gather you're year 1 and year 2. As you progress in your studies, you'll learn what a programmable logic controller, i.e. PLC, and a distributive control system, i.e. DCS, do. Okay? And they're used extensively in controlling and monitoring and operating mechanical, electrical devices. Okay? And it saves you having to think what you do next under that. That's what it's doing the whole time. And they all like to think they're different. Some like to think they're special. It's like cars, isn't it? A Toyota is more special than a Hyundai. A Hyundai is more special than a Rolls Royce. And a Rolls Royce is more special than a Lamborghini. And a Lamborghini is more special than a Ferrari. So which is the most special car? For me, it's the McLaren Sports. 390 miles an hour. Way. Okay? Made by a New Zealander. Or made by a New Zealander who owned the company once. I think his wife still has got shares in it. Obviously, he's passed. Okay, so that's what we're talking about. Everyone is special. It's just like a trade. Just like operator. There's an operator. There's an electrical technician. There's a mechanical technician. There's an instrumentation technician. We're all special, but we're more special than you. Here's a scary thought. To operate the plant, it takes all of you. To operate the plant, you have to work as a team. Otherwise, you can't operate that plant because no one knows the right answer should it fail in that respect. Okay. Now, do we go back this way? Oh, okay. Works the same too. All right. Now, here's a quick. Who here knows how your brain works? Do you know you have a conscious memory? Do you know you have a subconscious memory? You definitely know you have an unconscious memory. That's when you're asleep. Okay. A conscious memory means what? There's only one thing you can do at any given time. I don't care how good people say they can do multiple tasking. Your brain in the conscious state can only do one thing at a time. Does it very quick though. Far quicker than any computer. There's a scary thought, eh? So there's that, all right? And then there's the subconsciousness, and we've talked about that already. This thing can do 7 things at any given time. You can be listening to me, you can be talking on your phone, you can be turning around, not watching where you're going, all those things. You're driven by what's around you, okay? And what attracts your attention in terms of that. However, computers don't work that way. Is that right? Computers go through a process, okay? When you turn the computer on, it does a power on diagnostic check. You've experienced that, eh? You get up in the morning, your computer is turned off, you turned it on, and it just sits there and you think it's doing nothing. But it does a whole lot of diagnostic checks, all right? The first thing we do when we wake up from unconsciousness is straight for the phone. Okay, my father used to go straight for the cigarette. Okay, in terms of that way back then. Okay, so it does a whole lot of diagnostic checks. Once it does its entire diagnostic checks and does what it needs to do, it then goes and checks. Okay, it detects the state of all external inputs and output and updates the input table. So here it goes out and checks all the inputs and updates the table. Now the table is another way of saying a cell of memory in your brain. I won't tell you how many cells you got because we're all different. Not really, we all have the same number. Some uses more than others in terms of that. Okay. And then it goes to what we call the program scan. Now for us, they're starting to think, what am I going to do today? Where am I going to go? What I need to do? What I got to take to school? Do I need WIS books today? What's my study lessons? That's what your conscious memories, unconscious memories telling you. It's based on what you thought the inputs are that you've got to do today. You may have read what you got on the timetable, those sorts of things. And then it sends everything to the output. It goes here, activates the output devices. Once we've transferred it to to the table. And that's when you suddenly see all these people running around like idiots. What am I going to do now? I've got to get, I'm out of here, gone. One of the crucial ones that I discovered that they're late. All right, by looking at the time in terms of that. And then if it's a programmable logic controller or DCS, it communicates all terms. So around here, it does a housekeeping. It says, okay, let's update everything that's on the server. You know what a server is? Or what do they call it? What do you call it? SharePoint files in the cloud computing. Who's heard of that? Where do you store your photos? Do you store it on your iPhone or do you store it in Google or in Apple Cloud, as they call it? So you have no idea where they're stored, do you? All you know is you can access them. Okay, in terms of that. So that's what it's doing. And then it starts again and goes through that whole process continually from the time you put power on it till your time you take power off this controller. Okay? Difference is it does it in milliseconds. What's milli? 1,000th of a second, is that right? Who here can comprehend what a second is? Can you comprehend 1,000th of a second? You can't, can you? Your brain can't comprehend that time in your brain. It can do it, but you cannot comprehend it. It's very even hard to see a second. You have a stopwatch and you go press go, 9 times out of 10 on the latest phones, it counts it in milliseconds. That's how fast it's going. That's how fast that circuit is going in terms of that. Okay. We talked briefly about control loops. We talked about open control loop, what it's doing. We've talked a little bit about the basin. What's another common one that you have all the day? Who uses a microwave? That's an open control loop, isn't it? You put it in, you close the door, you press the seconds, and it cooks. If you've got a smart one, you close the door, you press reheat, and it reheats. Okay? And you think that's a computer. No, it's not. It's governed by the amount of power that PLN provides to your circuit. And PLN, like every other power company in the world, offers you plus or minus 10% of the voltage. If it drops down from 230 to minus 10%, you're only getting around 202, 203 volts, which means for those of you in electrical, you haven't got as much current because the resistance is the same. Therefore, your heating effect drops. which is why you suddenly go, why is this taking longer than 20 seconds to heat? Okay, that's what it's all about. All right, so we've got to think like that. And then you got your control loops. And we talked a little about this. This is your closed loop control. Okay. Storage water tank. What we're measuring here is level. Common thing that we do inside our plants, our control plants. Always measuring. Remembering, for those of you who are into mechanical engineering, all right, what do we know about a centrifugal pump and mechanical engineering? Most of your pumps are centrifugal pumps and geothermal. It can't suck air. Is that right? It must have what we call a head of water or inside the actual impeller, because it spins at a very fast speed, doesn't it? Direct drive to a motor, it can spin at 1400 RPM, maybe 2800 RPM, real fast. In terms of throws it out, which is why we are always measuring the level here to keep a head on that process there. Okay, so level control valve, level controller. So here's our level controller. Here's our control valve, and here's our transmitter. It's measuring the level. It does that by pressure in terms of that. So it's a pressure transmitter, but we recalibrate to measure level. And that makes sure that that tank there has always got sufficient water in it to enable that pump to pump out in terms of that. And that's what you need to understand as an operator when you're doing your checks. Okay, what's the difference? This is where things get really complicated, okay? Open loop is the most simplest form of control and the cheapest, all right? But it doesn't do any of this. It doesn't continuously adjust. You imagine if you had to continuously adjust the level input to that silo that we had just before that balance tank. How often you'd be sitting there adjusting it. And you've got all those other things you've got to control at the same time. All right, so you can only do, so that's why they go for closed loop control, okay? And the thing that we're looking at here is it never is fully open or fully off, depending on the process it's controlling. And when it's in the continuous or discontinuous state, it continues monitoring. Here is the key disadvantage. The key is the cost. People often say to me, so why don't we have all these things in the sky and all that sort of stuff, cloud computing? It's called cost. The plant to build is probably in the millions of dollars. The fully automated plant in today's standard is also probably in the millions of dollars. Okay, there is no difference in terms of that. We've talked a little bit about input and output signals. Okay, inputs are about providing, outputs about giving the process the ability to adjust. So when we have control signals, we can have on-off control and control it, which is what that water heater was doing. Remember the water heater and the electrical in your house? It's a controlling device turning on-off. Okay, if we wanted an accurate temperature, say you wanted it at 72 degrees shower, you probably don't, but if you did, then you'd have around about another $8,000 to put a proper controller on it that enables you to monitor it that closely. We don't need that, so we just do it that way, okay, in terms of that. However, If we want a continuous, then we've got to think about this. Okay, what are we trying to actually think about? We got those continuous signals in terms of that. So we've got to be careful. What we do need to know, although this is a very technical topic in itself, and more than happy for you to check that out when this, because I'll be leaving it here and you can read it. Proportional integral derivative, that's key fundamental modes of control action. Proportional. Do you know what the word proportional means? So as you in instrumentation, you should be listening now. This is fundamentally your bread and butter, isn't it? How do you adjust a response within your feed? By adjusting the proportional, the integral, and the derivative. So, what's proportional? If you're going 100 miles an hour, someone walks out in front of you, and you hit the brakes, so as to not hit the person that walked out in front of you. There's 100 meters between you and them, and you're doing 100 miles an hour. You're going to jump on your brakes. What's going to happen? You jump on your brakes. Your car is going to do what? Apart from squeal from the tires locking up, is that right? And you're going to go, and you're going to skid, aren't you? Okay. You made a proportional response. You jumped on your brakes. And it went, and carried on, didn't it? Didn't stop. Just, and suddenly you're trying to steer something that's just skidding. Is that right? Okay. What's integral? Same story. What's integral? If it gets to the point where it's in a position where it can adjust, it can bring it back down or bring it up so it stops. What does derivative do? It gives you an instantaneous response. If you set it right, it goes, stop, stop, stop. It's called ABS braking. Who's heard of that? ABS braking, where your brakes go on and off. Okay. Who's ever jumped on them in an emergency in the car? It's got ABS braking. You hear this tremendous amount of noise. Are you aware of that? Huge noise. Sounds like someone clapping in the background. And you take your foot off the brake going, what's wrong with the car? And you go bang into what you're trying not to hit. It's about slowing rapidly that car down. And each time it slows down, it has proportional response and it has integral response. So it's always checking where I am so that I can control my braking. And if you've got the right amount of brake pads and the right amount of energy, you can stop a car at 100 miles an hour within a given time frame. Remembering energy, you can't get rid of energy, you can only use it somewhere else. So you're using it on the brake pad to try and slow you down in terms of that process there. That's a simple way of saying proportional integral derivative. More in terms of that little clip there, which we'll leave for you to have a look at. Here's a scary thought. Evolution of time. When I first started, that was the power station. Then over time, even though it was built in the 60s, it doesn't mean to say it came into New Zealand. Then it went to that. Then it went to that. And now we're into that level where we're doing the process from there. It's just evolution of time. It's just like your phone. Remembering years and years and years ago, my mum, who lived till she was 97, had a phone when she was only 3 years old. And it did exactly what the phone was supposed to do. Hello, how are you? Nice to see you. There's no such thing as computers. When she was 3 years old, she rode a horse to school each day. It was a scary thought, eh? In New Zealand, it was very scary to think that someone rode a horse to school each day. So outside the school was the old Western rail, and he tied it up. Okay, in terms of that. Okay. And then eventually we are where we are today. Now, your cell phone, your smartphone, your Apple, your Samsung, what's its primary function? Hello, how are you? That's for you to ring someone, isn't it? How many of you actually ring someone on your cell phone and talk to them? Or do you go, oh, I'll send them a text? Oh, I'll tell you what, I'll just do Facebook. More important, they go WhatsApp. And you're going, they're not responding to me. Well, probably because I got their phone turned off. Okay? I'm an old-fashioned time. When my children want to get hold of me, I ring them and talk to them. Why don't you just give us a WhatsApp? No, I want to talk to you. You know what my answer really is? I love you so much, I want to talk to you. And then they go, oh, Dad, you sound sick. All right, here's the control room. Much as you think all these screens here are for the operator to play on Facebook and do all that, they're not. His screen is his phone, which he hasn't got in his hand. Those are the screens controlling the plant. That's the screen that the site management, which is based in Hamilton, and this plant's based in Taupo, can read data. That's the alarms of people who walk on the site, and where we monitor key things, so key pressures, key temperatures that you can read, and that's a spreadsheet of the faults that are coming up, how many faults are there, and what should I do about it? Is that fault important in terms of that process? So you're working the whole time in that, okay? So all this leads to this thing, this slide. The whole time you're operating the plant, you're doing this. I'm operating the equipment, I'm monitoring the equipment, I'm using these principles of control, and I'm here to protect, okay? If I'm in the maintenance teams, I might be doing some configuration, I might be looking at fault diagnostics, and I might be looking at maintenance schedules. If I'm in the engineering function, I'm looking at the engineering, I'm logging actions, archiving, I'm checking the alarm systems, and I'm data logging as appropriately. And I actually go back on historical data to see if it's trending a common fault. That's what I'm doing. The operations, you're here. Maintenance management are in here. And here you're talking with the engineers. Right? No one is more important than the other in terms of that process. We've covered that. So we'll skip that. We've talked about that, of what a DCS does everything else does, so we'll skip that. Now the alarms. These are operation worst nightmare are alarms, because you got to do something when they ring, when they go off. All right. When someone says to you, we're having a practice fire drill today, how important do you take notice of the siren when it goes off? Or do you go, oh yeah, another fire drill. Right, we've got to walk out the building and go to the part where we're supposed to meet, is that right? So you'll walk out, get your roll taken, you will then turn around, come back in, and that's a fire drill. Exciting, eh? Who's actually pressed the fire button to say they're watching a fire? I have. Believe me, in an industrial environment, when you see an electrical explosion and it explodes out of a main switch and you press that button and no one expects it to happen, the whole staff on that site change their attitude to an alarm, because they know it's not a practice. And you don't see them walking slowly out, you see them going to their designated posts very quickly. Okay. But alarms are something that we become so familiar with that we forget about them. What's the most famous alarm we forget about? It's on your car. It's called the horn. Doot-doot. Doot. Versus a truck going, oh, and you get out of their way, don't you? Okay? With the big air horns. All right. These are different alarms that as operations you come to learn that you have to abide by. There's a shutdown alarm. All right? So if you've got the piece of equipment that has shut down deliberately or as a result of a trip, it's going to alarm. And you have to take notice. Because somewhere along the line you may have to do something, right? There's the absolute alarm, okay? When you get to high or low level alarm, all right? Which means you've gone past a recommended level, all right? Or light below. The trouble alarm. People go, whoa, trouble, what does that mean? Okay? That's your vibration. That's the temperature of your windings. That's the temperature of the liquid. It's a trouble alarm. It's causing you things. Deviation. So sometimes in terms of this, you have a deviation alarm coming up. Well, this thing's coming up to the very high level. We need to say, well, actually, you got a problem. It's growing, it's growing, it's growing. Bang, it's hit you. And if you haven't done something back here, you could have prevented that, okay? Memory alarm. So that's a memory alarm where it's saying, actually, your set point's been passed, we're going to stop you. Remembering the plants will stop you from doing things. It has to, in the interest of environmental, health and safety to people, and damage to the plant. We'll skip that one. Oh, now, interesting. Well, the pros and cons of there is a group of people in the world who are trying to eliminate humans from operating anything. And this is their version of what the pros and cons are in that respect, okay? Much as we can remember, recognize complex transient conditions, we fail under conditions of overload and understimulation. And some of you are feeling that way now. You're understimulated. You're not listening. You're away. And that's all right. We understand this. Okay, so we keep moving in terms of that. Okay. So we need to think about what else we can do. We'll just skip that one. Okay, here's a few other things. that we need to watch: chemicals, purity of steam, pH levels, levels of biocide, has it in two-phase flow. Now, who's ever heard of a system? If you're inside your car, are you sitting inside a system? You are, aren't you? What you want is your car to take you from A to B, is that right? And if you're young and enthusiastic like some of you look, you want it to do as quickly as possible, as safely as possible. So you hop in your car, you turn the key on, start the engine or your motorbike, and you let go. Okay, as quickly as possible, what we're looking for in terms of that. So your geothermal plant has a whole lot of systems. And one of the systems I just think we should allude to is the main generator. So all these are systems. These are things that the geothermal plant has to do and has to have for it to work. Let's look at the main generator. Now, who thought the main generator had all this controlling it? Interesting, isn't it? Just to get the main generator to work, over and above putting the mechanical energy in it. You imagine how much instrumentation's on that. We need to step up there. Oh, there it goes to the high voltage. But here's all the protection of that. So protection is always about, if there is a fault in here, we don't want it to go out there. And if there's a fault out there, we don't want it to come in here. So that's your protection scheme, two ways across the board. Here's your control room, and there's all your process. So all of this is just protecting the generator. It's not protecting the rest of the plant, it's just protecting the generator. Okay, so it is quite a complex little process in terms of that.
Sorry, Chris, you have 10 minutes left.
Yep. Now, here's what we call the parastatic load. So here is what the kilowatt is. You get? So that's how much is coming out of the wellhead. And this load here, all of this is the load. And this is all we can generate to the power grid, because the load is taken up by all of these bits of equipment. So geothermal power plants don't need PLN energy to run. Okay, it's run all through its own turbine systems. And that by doing that, we can only, in this particular example, generate 20% of what we get out of that, because of all the loads that we hear. And the biggest load is the brine coming off the turbine. It's energy, it's not power, okay, in terms of that process here. All right, so let's finish on a video. This one here, on the tungsten geothermal power plant construction video. Goes for 7 minutes. I just got to look at the puck here to say 7 minutes. Okay. Again, notice when it starts and notice when it finishes as you go through that. And notice the timeline it's telling you. So from the reservoir, to putting the reservoir, putting in load, it slows us down to see how much energy is in it, to when it's generating power. Oh, look at that. We're away. Actual true story. Okay. Thank you for that. I'll hand back to our moderator. I'll hand back to you now. All finished. I'll come up there.
Okay. Thank you, Pak Chris, for your insightful presentation. As always, I am amazed with your energy to come around. Okay. The next session is Q&A. Please remember to introduce yourself and please raise your hand and tell your study program and student identification number. Okay. One and two. This one, three students. The woman first. Yeah, yeah. Okay.
Thank you for the opportunities, sir. I want to ask about the geothermal first. In the geothermal production process, there are various problems. One of them is silica scaling. And how is the silica removal process? And which is more economical, single flash or double flash for silica scaling problems in injection pipes? Thank you.
You get it?
Not all of it.
He asked about the silica problem in geothermal and how to solve it. Yeah.
Problems.
Yeah, problem with silica.
Silica.
In pipeline maybe.
Yeah. Okay. If I could answer the silica problems, I'd be the richest man in the world. Silica is a natural event happening within the actual geothermal process, brought about by the chemicals that's inside the actual steam in terms of that process there. There's different ways to resolve it, from pouring acid down the well hole, although that's not really where it occurs. The main process is where it occurs is when it reaches above ground and it gets into the steam pipes and into the key areas around the turbine and that process there. So they do have processes around some sites, which is about acid. But importantly, what they're looking at now in New Zealand is how to extract that silica before it actually gets to where the dangerous levels are. So there's a company, and some of your Indonesian people are going down to a conference in Taupo, New Zealand in early July, where a company is showing them how they extract the New Zealand silica and then how they use that silica to make a profit by selling it to a Japanese market. So there are ways around it that's far more complicated than an electrical engineer like me knows, because it is a common thing there. But I'm sure if I talk to my friends back in New Zealand, I can get the answer of the process they're now using to remove silica from the steam.
Okay. Okay. The answer. Okay. The second question. Okay. Yeah, please introduce yourself.
Yes. Okay. My name is Regan Radian. I'm from Mechanical Refinery Engineering. And I would like to ask about what are the disturbance variables in a geothermal power plant sensors and also the
Hold on,
mechanical
hold on.
component.
Please slow down. Yeah.
Okay.
Slow down.
What are the disturbance variables in a geothermal power plant sensors and mechanical component? And how can one eliminate it? Thank you.
What about mechanical?
Okay, let me repeat it. What are the disturbance variable in a geothermal power plant sensors and mechanical component? And how can one eliminate it? Thank you.
Disturbance variables.
Oh, yeah.
Dis-
What the?
Disturbance variables.
Oh, yeah.
Yeah. All right, the disturbance variables in geothermal. Funnily enough, steam being one, because steam in geothermal is dirty steam. And depending on the steam field that you're operating in will depend on what you have to do. Steam in New Zealand is pretty clean. We only have one form of steam in the ground. In Indonesia, geothermal, there are 7 different types of steam fields you can have. And they all have their different variables and processes in which they need to eliminate them. And that could be from chemical, it can be from straightforward minerals, and it can be from the actual low pressure drop as it pulls up in terms of that process. Inside the plant, there's a whole lot of other variables that can happen. One of them being the environment, ambient temperature, especially on the cooling tower system, has a huge impact. And certain steps have to be taken to minimize that effect. To some point where they actually thought they'd cover the geothermal cooling towers to stop some of the environment from heating it, but in actual fact, that caused more problems because they're overheating the motors and overheating other devices. So each case is a case-by-case study by the engineers at the time and a continually monitoring process. So variables are condition of the steam, the condition of the environment, and then ensuring that the condition of the equipment matches what the design specifications mean in terms of that process there. Hope that answers your question.
Okay. The next question with the uniform, jacket uniform. Yeah. Okay, you are. Yeah, yeah.
Okay, sir, thank you for the recognition. My name is Raihan Akbar Ramadan. I'm from Refinery Engineering. Now it's my 4th semester here. I have 2 questions. The first question is how much New Zealand will depends on geothermal as the main power supply for the country? And the second question is how do you look at Indonesia at the future as one of the most country with a geothermal potential?
New Zealand?
How about the geothermal production to support the electricity in New Zealand?
Yeah.
And the second one is the geothermal potency in Indonesia. Yeah.
Yes.
Yeah. How about geothermal potency in Indonesia?
Okay. Okay, so in New Zealand, we are very, very fortunate. 65% of our electrical energy comes from hydro dams, which means that it's a renewable source because like Indonesia, at times we have rain every week, which means our lakes are completely full. Geothermal has been brought about because that means we've only got one set of base load, hydro. By having geothermal plants, we've now got 2 sets of base load, which means that even though we are like Indonesia, the cost to build a geothermal plant is extremely high. we are pushing forward for at least another 10 geothermal plants to be built in New Zealand over the next 10 years, 10 to 12 years. And that will increase our geothermal energy from where it is now to doubling its size, which brings it up to equal to about half of our hydropower. Plus, it'll mean that we will be a clean and green by the year 2030, which is the climate change act that our government has bestowed upon everyone around energy usage. In Indonesia, there's a lot of support for geothermal. The biggest obstacle at the moment seems to be the ability to find someone who can drill enough wells to enable them to be either given to a private organisation to turn into a power plant, or B, to a government liability company like PGE or Geodipper to turn in the energy into electrical energy. But at the same time, the challenge is that your population has just reached roughly around 300 million, if I recall, which means that you're still growing in terms of population, which means your population your electrical industry has to keep up with the population. That takes everyone, include all companies, governments, and everything to enable that to happen. Hope that answers the question.
Okay. Okay, thank you, Chris. And the next question from this side. Okay. A microphone, please. The third row from front. This one, this one. Raise your hand. Raise your hand. Yeah. Yeah, yeah. Okay.
Check. First of all, let me introduce myself. My name is Bayu Zakir Rifat. I'm from Refinery Engineering. Thank you for the opportunity, Mr. My question is, what's the reason, advancement, or breakthroughs in geothermal technology? And do you believe that this geothermal industry can hold the most promise for revolutionizing the industry of efficiency and sustainability? Get it?
Get that?
What do you think about the geothermal is the most promising about the efficiency and effective in energy, clean energy? Maybe you can share about that.
Sorry, say what? Okay. Geothermal energy is an untapped resource in every other country except Iceland. Iceland uses geothermal energy to the extreme gear. Oh, yes, they do produce power with it. And they're the only country in the world that is totally renewable electrical energy. However, they also use renewable energy to feed and build infrastructures that keep the Iceland community going, such as hot baths, and remember, Iceland's in a very cold place, hot baths, hot tubs, but importantly, growing food in large greenhouses, because they can heat that particular energy, removing minerals, and they're now looking at removing not silica. They've discovered that there are the batteries that use lithium. Lithium is actually inside geothermal as well, so they're now extracting lithium out of that. New Zealand's doing it, but Iceland is the leader in that sort of process as we go further afield. So by using those multiple different ways and use means that geothermal energy is becoming more and more adverse and widely known to the general public. There's still a fear of geothermal energy because it comes out of the ground, but it's starting now to become a very, very potent energy force that's waiting to be explored further.
Okay, you got it? Okay. The last question, maybe from woman. This one. This one, the second row from front.
Thank you for your opportunity, Mr. Chris Stewart. My name is Tita Avila Margaret. I'm from Instrumentation Engineering. In a geothermal power plant, key parameters such as temperature, pressure, flow rate, seismic activity, chemical composition, and equipment vibration are closely monitored to ensure optimal performance and safety. So my question is, what are the key parameters monitored in a geothermal power plant to ensure optimal performance and safety? Thank you.
The key parameter. There's one very key component in geothermal energy for electrical in terms of what it's trying to do, and it's not the generator. It's the condenser. And the ability of the condenser to pull the used steam through the turbine in an effective manner to enable it to keep above the speed that it's required. And as a result, also to disperse that hot steam away. So if the condenser is full, then the geothermal turbine won't work properly. But if the condenser is kept to its set point, then by pulling these steams through the turbine, we can actually increase the rotor speed, which means we can generate more power. So that's why the most important part of the whole process is the condenser, or it's the cooling system. So the condenser is part of the cooling system, the hot well pump's part of the cooling system, and then don't forget the actual cooling towers. That whole thing has to work, that whole system has to work to the design specifications as per required by the builder at the time. So that's vital. That's the key one you must measure.
Okay, get it? Okay. Okay, thank you, Pak Chris. Your insightful presentation. Give applause to Pak Chris Stewart. Okay, before we wrap up, could you give to our student last statement about how they're faced to the industry or etc. about especially in energy sector or geothermal? Maybe one sentence.
Oh, closing statement. Closing statement. Oh, okay. When I look around here, I see people who are a little bit older than my granddaughter. That's a scary thought, eh? And her learning journey has only just started in high school. And we often talk about what she wants to do. The key is, for me in geothermal energy is there is an opening in geothermal energy for the likes of everyone. The world is pushing for renewable energy. The world is pushing to find one that is less impact on the world than the other, but maintaining that energy through that process. So I would recommend to anyone is to study and look at the opportunities inside geothermal industry, because there's as many opportunities in there than what there is in oil and gas or coal or whatever. It's about what you want to commit to the environment within yourself. Okay? And that's what I tell my grandchildren.
Okay, thank you, Pak Kris. I'm as moderator. Thank you for your attention and your contribution to this event. And the last, Assalamualaikum warahmatullahi wabarakatuh. See you later.
Okay, it is what an insightful presentations indeed from Mr. Chris Stewart. Thank you, sir. It is such an eye-opening information for a lot of us, certainly elevates our knowledge of geothermal power plant this morning. Also, thank you for wonderful speakers, Mr. Arya Dwi Chandra. Please give a round of applause. Okay, for those who active in questions and also discussions, would like to invite come forward to receive your gifts because you'd like to active in discussions and also give a questions. For the 5 persons that have a questions and also active in discussion, please come forward.
For all participants who has get their questions can come forward to receive our special gift.
Okay, Eliza, Regan, Rama, Egi, and Tita. Also, we have one remains gifts. Want to like resume our presentation today? Would like to give the gift. Who else wants to give a resume from the presentations?
This is the last chance to get another special gift. Only one remains. So if you guys want to make a resume from the presentation before, anyone?
Okay, guys, we have one remains gifts that has been not collected by you guys. So in order to collect that gifts, we want to do a resume from the presentations or feedback, resume or feedback that from the presentations. 1, 2, anyone else?
Okay, we count down up until 3. 1, 2, 3. Okay, so that was the last chance to get our special gift. Yes.
Okay, I think you guys giving up to collect the gift. So giving it a round of applause for the 5 persons that have active in discussions. Okay, we would like to invite Mr. Chris Stewart to award that nominations that the active in discussions to give the present.
One by one, sir.
Okay, take photo together. 1, 2, 3, cheese. Okay, thank you very much. Please take back to your seat and we would like to continue our events today.
Okay, moving on to the next agenda. As a form of our gratitude towards the willingness of Waikato Institute of Technology in maintaining good cooperation with Pemakamigas Cepu, we present this appreciation gift, which will be given by our Director of Pemakamigas, Mrs. Erila Indriani. We also invite Mr. Chris Stewart as our speaker, also representative of Waikato Institute of Technology. For Mr. Stewart and Mrs. Erila, please come forward. This appreciation gift is a
Okay.
symbolic form of a good relation with the Kamigas. Thank you, Mr. Chris and Mrs. Edila. Please return to your rightful seat.
Okay. Miss Erdila, maybe we can stay in the stage. Also, would like to express our gratitude to New Zealand Embassy for attending our events today. We present this appreciation gift, which will be given by Mrs. Erdila as the Director of PM Akamigas. And also, we invite Mrs. Indirawati. Please come forward to receive the appreciation gifts.
This appreciation gift is a symbolic form of a good relation between Pemakamigas and the New Zealand Embassy. It is hoped that this cooperation will persist for a long run and improve further.
Okay, very well. And also for the last sessions of our events today, I would like to invite all of us to stand up to take a documentations and also the invited guests to stand up and come in the center to do a documentations. Please stand up.
For all the invited guests, please come forward to a documentation session.
Maybe the invited guests may gather in center. Be ready, guys. 1, 2, 3.
Okay, one
Okay.
more time. This one is a freestyle pose.
Freestyle, freestyle.
It's a freestyle pose, everyone. 1, 2, 3.
Okay, very well.
Okay, thank you.
Okay, for all the participant can remain seat.
Documentation session will mark the end of today's event.
Thank you so much for the attention and enthusiasm for all the participants have to come to our events today. I'm Dami Pasca.
And I'm Safira Putri. Apologize if there were any mistakes during our event today.
See you on the next One Day with Expert.
Have a great day and
Let's energizing green future with geothermal energy. Thank you very much. See you soon, guys.